Hi, it's Steve Hargadon, and if you're in the Americas, we're closing in on the end of the second day of the Global STEMX Education Conference. Wherever you are, we sure hope that you're enjoying these sessions. We're having a blast. Tim Bell is here as our keynote speaker. Tim, welcome.
Thanks, Steve.
Thank you for making the time. Thanks to our sponsors and supporters for the conference, especially thanks to HP and ISTE for making this possible. This free worldwide event that puts an emphasis on practitioner sharing. We think it's a great thing, and we really like these folks. This is a chance for you to indicate where you're participating from. Look to the left of the map. You're looking for a star icon, the second one down. You're going to double click on that, and you're going to click on the map. Of course, we have New Zealand here. United States, a couple of New Zealand. Peggy's giving me a hard time because in previous webinars, New Zealand has gotten cut off the map inadvertently. So let us know in the chat where you are, the time, the temperature, anything that would be fun for Tim to know. And Tim, I'm now going to turn the time over to you.
Great. Oh, well, thanks, Steve, and thanks everyone for joining in, especially I think it's a Friday night for the majority of you. So what I'm going to talk about this morning for me is what we've been doing in the last couple of years in New Zealand high schools. And it's been a pretty exciting time because we've introduced computer science as a subject, and I'll spend a little bit of time just talking about what we mean by computer science because it's more than just programming, and it's something that's been missing in our high schools, and we've been campaigning for literally about 30 years to get it into schools. There was a little bit there back in the 80s. And it's a problem that's worldwide. In the UK, this month, it's just being introduced as a subject in schools, and I know in the States that it's quite an issue. Some states and some areas have managed to get it introduced, others are struggling, and others it's been quite a negative, in that it's been a lot of pushback. But just before we get going, I thought it'd be good to do a quick poll just to figure out who I'm actually talking to in terms of where you're at. So I think it's above the chat. There should be a poll appearing above the list of people. There it is. And if you can just sort of choose where you are, what's your main role, A, B, C, D, or E? Oh, great, everyone's what they're doing here. So let's make it visible. It didn't work. Okay.
Tim, do you want me to do that? You can focus on moving forward.
That'd be great. Thanks, Steve. That'd be cool. Just looking at those letters, we've got quite a few of other. Actually, maybe you'd just like to type in very quickly how you would describe your otherness. And then that would be great. Meanwhile, I'll just move on to the next poll. I've just got 3 of them all together. So this one is really just where you are at with the programming thing, and in particular, are you teaching programming and had lots of experience with it, or is it a new thing for you, and so on. So let's just set up another poll. And just by way of background, of course, what we've been doing, the big focus, and what I'll be talking about a lot, is the last few years, we're taking a lot of teachers who have basically got into computing, many of them through typing. They've been typing teachers, way back, and then have had to learn how to do word processing, and now are suddenly finding themselves teaching programming or computer science and so on. And it's a matter of, where do you start if you've never come across that sort of thing before? Okay. So that's very useful, and we'll just quickly go on to the next poll. So I'll just set this one up. And again, this is computer science. So this is, let's say, computer science except for programming. And so this would be things like algorithms and artificial intelligence or formal languages or interface evaluation and things like that. And again, the key thing that we've found is that we're spending a lot of time working with people who would very much put themselves in the A category. And that's been a lot of the problem internationally, of course, is that most administrators are in the A category and most politicians are in the A category and most teachers are. And so it's very, very hard to get things off the ground because people often mix that up with programming, which is a part of computer science, or in particular, mix it up with just learning how to use computers. So let's move on. Thanks for those responses. That's really, really interesting. So one of my key things has been captured in this quote by Edna Kerr. The greatest tragedy I know of is that so many young people never discover what they really want to do. And for me, what we're doing with STEM, and for me in particular, computer science education, is not trying to create a flood of computer scientists or a flood of engineers or anything like that. Industry would love that, and that would be just great. But really, there are so many students I come across who got into computer science by accident. They didn't realize they were good at it. Probably my best student ever hated computer science at high school, or at least she thought she hated it. She's now doing a PhD at Cambridge in computer science and rewriting Java, and absolutely loves it. And she only got into it because her boyfriend was doing computer science, and she took an interest in what he was doing and suddenly realized it was just her thing. And so I think our big goal here is really to expose students to these ideas. But the big challenge is, how do you expose them in a way that doesn't put them off? And of course, the things that affect that is not just sort of having, cool stuff like let's do programming in Scratch because that's really fun, and when you grow up you'll be able to do super duper Scratch programming or something. It may not even be it's a good introduction. But also teacher confidence is absolutely crucial. If you have a teacher who is not confident, who doesn't like the subject, then no matter how interesting the subject is, they may tell the kids basically this is something you shouldn't be interested in. So yes, what is computer science? And computational thinking is a very good point there too, Dee. So I don't know if anyone quite knows what computational thinking is, but what I'll do is I'll try and touch on a few of the ideas surrounding that. And so I like to actually do stuff, and if we were all in the same room, I would actually get some of you to have a go at this activity here. So maybe just type in the chat if you've come across this activity before. Otherwise, I'll explain it in a bit more detail. But these girls here are about 12 years old, and what they're doing is they're working on a parity error correction system. So the cards here represent the black and white are obviously the zeros and ones on a computer, and it doesn't really look like a memory game. And the way that it works, it's actually, we sort of sell it as a magic trick, and particularly for 12-year-olds and younger, they just can't believe that this works. And this is one of the things I love about computer science, is it's full of things that you wouldn't have thought that they could exist. And so the way this works is one of the girls has put down 9 by 9 of those cards, so all but the outer row, and they're just completely random. They'll represent, there might be some data or something, but for the trick, you just put them down randomly. And then the person running the activity, they say, well, to make it a bit harder, I'll put an extra row along the top and an extra column down the right. Now, of course, they're not really making it harder, they're actually making it work. And the trick is that you add the colors along the top so that every row has an even number of black squares in it. So you'll notice, for example, see if I can get a pointer thing going here. If that column between those two dots there, can you see those okay? Those are, there's exactly 4 black cards there, and then the next one, there's exactly 4 cards. So, thanks, Steve. And so if we go to, I've got a numbered version of it here, it's the same thing numbered. See if anyone can spot which card, one of these cards now, has been flipped over. Okay, and this is the memory thing that impresses people. Is while you're looking away, someone flips a card, and you come back and you say, I can tell which one's flipped over. But in fact, the way that this works is that even this group of people that I'm talking to spread around the world can look at some cards that were put together by some girls at the end of last year and say, I know which one they flipped over. Can anyone going to have a go at where there's something wrong? Okay, so Steve's having a go at A1. Now bear in mind that that column originally had an even number of black cards in it. Okay, and it still does. So probably nothing wrong there. Yep, Jackie's got a clue there. But if we go along here and we look at column G, you'll notice that there are 5 cards in that column. Now, when it was set up, it should have had an even number. So one of them has changed. Kim's got it. Okay, prize goes to Kim, because column G is wrong and row 6 has also got an odd number of cards in it. And so based on that, we know that G6 is the one that was flipped over. Okay, so yeah, it is actually, yeah, it will actually, yeah, it's an even number of black cards, but hopefully this makes sense. And in fact, Jackie's put up a link to where you can find out more about it. And Kim has too. So it's one of our unplugged activities. It's computer science without computers. Now, the big point here is that, first of all, this is astonishing to young children. In fact, it's quite astonishing to a lot of adults that you can figure out what's been changed. And every piece of data on a computer uses a system like this to make sure that if things accidentally get changed, it's got half a chance of actually fixing it. If they get a scratch on a CD or a little magnetic particle on a hard disk fails, then it doesn't just read the wrong data. At least it can tell that something's wrong. There's an odd number in there somewhere, and maybe it's even got a chance of putting it right. And so that's the kind of idea that we want to say to students, well, if that kind of makes sense to you, if that's exciting, then maybe you think like a computer scientist. And we've got a club which we've been running for younger kids, and they sent me this photo and they said, which one of these cards has been flipped over? There's over 500 cards there, but if given enough time, you could actually figure out which one has been flipped over. So that's one cool thing about computer science, stuff you can do that you might not have thought was possible. And then at the other extreme, there are things that you might have thought were possible. And so here we have a traveling salesman problem, it's called, where we've got a bunch of cities, in this case 7 cities. And by the way, I'll just put up a link for this thing. The goal of the traveling salesman problem is that you need to visit every city once, but you want to minimize the distance going around all of those cities. Now, we've got the program at that link that I've just put there. It's one of the, if you scroll down a bit, you'll see it. And what it does is it tries out every possible route. So it'll start at city number 1 and try all the possible ones to go to next, and then all the ones you can go to from there. And you can see, and by the way, we've got a local company that makes millions of dollars off this problem. They actually run these programs for American companies like Coca-Cola and DHL who deliver. They have to go around these routes dropping off Coke bottles, really important thing to do. But this program I've written here would take 36 seconds to try out all of the possibilities. And that's for 7 cities, going around 7. Now, what I usually ask students, in fact, I'll ask you now, that's just going around 7 cities. How long do you think my program will take to run for 14 cities? Twice as many cities to try out. It took half a minute roughly for 7. Just type in a guess for how long you think it would take to, well, I'll put it differently. How long do you think your students would think it would take for 14 cities instead of 7? Okay, so twice as long. Yeah, okay. That's what they would think. And in actual fact, when we crank it up to 14, it takes 9 years, 10 months, 11 days, and so on. Because it's a combinatoric problem. Every time you add one city, you're actually multiplying the number of possibilities that need to be tried out. And if you follow that link I gave you, you can crank it up and you can press the start button, which is kind of fun because it starts counting down and you can see that it's just completely hopeless. And by the way, if we go from 14 to 21 cities, often the students will estimate that maybe, oh gosh, that will take hundreds of years, or some will say even thousands. But in actual fact, it will take 3,800 million years on that program. Now, that's running on a web browser. It's running on a slow programming language. And so you could say, well, okay, suppose I had a computer that's 1,000 times faster and I use a programming language that's got lots of shortcuts in it and it's 1,000 times faster. How long would that take? And the answer is, I'll let someone type it in. So we're running 1,000,000 times faster than that. And it's running on so this would actually be on a supercomputer. Okay. By the way, it might run faster in your web browser. Maybe it's a bit early in the morning for this one, but obviously if it's 1,000,000 times faster, it's only going to take 3,800 years. Okay, so to try out all of those possibilities. So there's two extremes of computer science: something that you would have thought was possible that isn't possible, and then back with the parity thing, something that you might not have thought was possible, like just figuring out what's gone wrong, and yet it is possible. And so there are lots of paradoxes, and that's really cool from a teaching point of view. But these are all things that are happening underneath on computers. Well, just the idea that maybe you can't get a computer to try out every possibility. Well, it'll work, but you just got to wait a few million years for it to come up with the answer, and that's not good enough. So one of the problems we've had with computer science in schools is that people have been trained to be users, and Edward Tufte said there are only two industries that refer to their customers as users. And the other industry is not one that schools really train people to get into, and shouldn't be. Now, the reality is that everyone, nearly everyone, will be a computer user. You can't go far without using a digital device. So yes, we do need to train people to use computers, but what we're interested in computer science is how would you build something? How would you actually create something new rather than be forced just to use what you're given? And so what's happened in New Zealand is in 2011 we introduced some new strands into what's called digital technology. Well, in fact, it was restructured. So there are these 5 strands now that students can explore. And so there's digital information, which is a lot about using computers and spreadsheets and databases and things like that. Digital media, working with web browsers and working with video and that sort of thing. Here's the one I'm really interested in, programming and computer science. And we worked really hard to make the name programming and computer science, to really make it clear that, because a lot of people would think, oh, computer science, that's just programming and so on. And then there's electronics, which is digital electronics, and then computer infrastructure, which is building networks and putting together boxes and computers and that sort of thing. And this has been introduced into the last 3 years of high school, which are the ones where students are doing exams that will get them into universities and so on. Before that, the assessment doesn't really count sort of for lifelong qualifications. So although it's been introduced into the last 3 years, it's gradually filtering its way down lower, because teachers are getting confident with this material and realizing it's good to actually give students a little bit of preparation. So the key changes that have happened are that we've got what's called achievement standards, and prior to that, computing had been what's called unit standards, which just pass-fail. You either know how to look after a floppy disk or how to enter something in a spreadsheet or not. Achievement standards are what the top students, the academic students, really want. They want to be able to say, hey, I got a really high level, a really high grade, and the 3 grades in New Zealand are called Achieve, Merit, and Excellence. And so students are trying to get excellence to get those scholarships and prizes and get into really good courses and things like that. And so finally, it was possible in computing. It went from being a class for students, almost a babysitting class for students who weren't doing so well, to being something that the top students could aspire to. It contains real computer science, the kind of, I've given you 2 examples already, and I'll give you a few more as we go along. Accurate terminology, because the term computer science has sometimes been applied to word processing or programming and so on, and also just IT is such a vague term that people, almost everyone does IT of some sort, so what does that mean? And so cleaned up the terminology. And the amount of programming that students are doing basically gets them up to the level of a university that, so the first year of a university. So it actually gives them a bit of a head start at the university. Now, one of the key things, the absolute key to all of this is teachers. And a really important thing that happened is that the New Zealand Teachers formed this association, which has got every variation of the word computer and digital and IT in it, New Zealand Association of Computing, Digital and Information Technology Teachers. And they have been very active in sharing information, supporting each other, and it's taken a lot of support, because we're taking people who have, generally keen about computers, but really haven't come across a lot of these concepts before. And it's not that the concepts are terribly hard, but if you go and Google a topic like error correction or traveling salesman problem, you'll get way too much information, way too advanced use in the classroom. So this association has worked very hard to get teachers on board and help them along the way to produce materials and that sort of thing. And I'll talk a bit more about the teachers later on, but one of the distinctions, and now we'll try and actually do some definitions, what do I mean by computer science now? If we look at computer programming, that's building the software, and I often just use Google as an example. So here's the Google New Zealand page. It's basically one text box and one button. In fact, as soon as you start typing the text box, even the buttons start disappearing anyway. And so lots of people know how to use it, and maybe people could even write a program that puts up a text box and a button. But the real question is, how would you build something like that can search every web page in the world in 0.2 of a second, which is what they normally do, or even less. And at that point, suddenly you can't just you could write a program that, reads in everything from every web page and goes through everything on every web page, but it's not going to do it in 0.2 of a second. And so this is where the computer science comes in. And so computer science is interested in things like, how do we make it work astonishingly fast? How do we make it really efficient? That could include things like battery life on a mobile phone. You really don't want to use that up. How do we make it really reliable? I mean, has anyone ever seen Google search not working? And what would the impact be if Google search stopped working for a day? It would be world news. You want it to be really secure so that, like what you're searching, other people can't find out, or when you've set up a password or a login, then other people won't accidentally, get access to your material and so on. You want it to be really easy to use, and that's another aspect of computer science, is how do we develop things, and that crosses over with psychology a lot. You want it to be scalable, and there are businesses that have worked fine when they've got 1,000 customers or 5,000 customers, but then overnight they end up with 100,000 customers, and everything comes crashing down, and no one likes them anymore, and it's basically the death knell for a business. So you have to know, if I got 100 times as many customers, would my system scale up? It needs to be delightful. A lot of software needs to just make the user really pleased. It needs to do just what they need to do at the right time. Intelligence. Oh, good heavens, there's a URL for One Day Without Google. Okay, so the intelligence, if we look at that web page that I had, it offers to do the Google in our native language, Maori here. And again, there's a whole lot of intelligence behind that and a lot of work that needed to go into it. And it's visual, there'll be 3D images and things like that. And some of you may be familiar in New Zealand, we have Weta Workshops who've done a lot of the graphics for films like Avatar and Lord of the Rings and that sort of stuff. Which employs vast amounts of our students, by the way, which is nice for them to get involved in. So what we're interested in is basically, how do you take a huge challenge like that and build it? And computer science kind of answers that question. And it is tied in with computational thinking, but it's kind of like putting wheels onto computational thinking. Okay, so Jim says, what do you do to help young students see computer science hiding in their world? Great question. So a lot of, well, the answer is we're still working on it, but the Computer Science Unplugged project has been a really important part of that. And in fact, it's probably a good time to actually mention that. So the reason I got into education is actually about over 20 years ago, we started developing this project called Unplugged, where, in fact, I was asked to talk to my 5-year-old's class 21 years ago. And I didn't want to bring along a computer because it just didn't make sense. It was hard to explain computer science on a computer. So we came up with a whole lot of activities like that parity one that I was showing you with the card trick and so on. And there's a number of other activities there that just use cards and games and so on. But then the really important thing that we found beyond that, of course, is that then you need to relate it to something that they're actually using in the real world. And one of the questions, I think, is what would happen if this didn't happen, if people hadn't discovered it? And so that's always a really important follow-up to working with computer science. And it's also a real challenge. I mean, for 5-year-olds, it was mainly to make a point that you could get some of these concepts across. But as students mature, and particularly around the 10 to 12-year-old age, I think they're starting to understand the world a lot better, and they can see where these things are in action in the world. And the idea, I mean, I can get a 12-year-old to the point where they've got a rough understanding of how Google can do that search in 0.1 of a second and so on. It's not that hard if you've got the right tools for explaining it. But yeah, you're right, Jim. You've got to do stuff. It's very much about engaging students. So the structure of what's happened in New Zealand is that we've got these last 3 years of high school, 11, 12, 13, and these new standards have been phased in. In fact, the year 13 ones were phased in this year. Our year starts in January, at the end of summer. And so we're just coming to the end of having run everything that you can see on the screen here. And there is a lot of emphasis on programming, so there's sort of 2 modules. By the way, all of this here amounts to about 1/2 of a course, and that's it was partly for budgeting reasons that they couldn't put in whole courses and so on, but actually works quite well because it means it can be 1/2 of a course for something else like web design or video editing or something like that, which means that lots of students get exposure to these ideas. And after all, that's the goal, is not to teach them the ideas so that they become experts in it, but simply that they're exposed to the ideas and can see how they work. So that programming takes up about 2/3 of it, learning to program, but at each level they're also working with basic computer science concepts. Now, just to give you an idea, the impact so far, these standards are not compulsory, so schools don't have to teach them, and students don't have to take them or anything like that, and they can still get into university without them, at the moment at least, because they're so new. So in the very first year, we had 440 students pass the exam for computer science, and a bit over 2,000 passed the exam with the test for programming. And that, to give you an idea, there's about 60,000 students that could have done that if every school had offered it and every student had taken it. But the goal is to have it a bit like biology or physics or something like that in the school, where students can kind of have a taste of it and decide if it's what they'd like to do. So we're pretty pleased with those numbers, and in particular it's growing, which is the key thing. So you notice that last year 646 students did that, and in fact at level 2 more students took level 2 computer science than took level 1 computer science following on. So it's been growing. Right, so yeah, Jim, you've made a really good point that the curriculum is so packed it's difficult to add anything. What happens in New Zealand is that there's some core standards that they have to do, English and maths, and that's pretty much it actually. But beyond that, students have a lot of choice about how they put together a course, and therefore they can choose what direction they're going to go in. And so it's not too hard to offer new things, and it may well be pushing out. We may be taking a physics student into computer science, or someone who's going to do advanced maths or something like that. In terms of gender splits, actually I've got some. We've done some numbers on that, but it's around about 36% of the students are female that are doing computer science at the moment. Which is not great, but at the universities, it's about 10 to 20%. So it's actually way higher. And I think also, because we're only starting at year 11, which is about 15-year-old students, that's actually a little late, and things are gradually moving down to younger students where the gender issue is not such a big deal. So what we're finding is the earlier they start, the more they get involved. I'll talk a little bit more about the gender thing in a wee while too, because it is a big issue in computer science, and it's a bizarre problem that we have. But so the programming is pretty standard, but I'll move on to what we mean by computer science. So at level 1, what they're doing is they're comparing algorithms, and this is algorithms are doing the same task, and I'll give you some examples of that in a minute. They need to look at programming languages, and that's not learning to program. That is, what is a programming language? How does a programming language work? And how do we, yeah, in particular, what's the role of the compiler and the interpreter and that sort of thing. Now, it's not rocket science, but a lot of people, for example, a compiler, if you're doing programming in, say, Java, you need something that reads that Java program and makes it run. And that thing that reads it in is a program itself. And that's kind of a neat concept and a very deep concept that is covered there. And then a big part of this is also human-computer interaction, evaluating interfaces, trying to figure out what makes a good interface, what makes a frustrating interface, and how people can design ones that really help users. And that, of course, has a lot of psychology in it, which, again, that's there early, and it's particularly addressing the gender thing, because girls are generally a lot more interested in the human side of it, and boys can struggle with that a wee bit. But it's also intended for perhaps the geekier, more computer-focused kids to realize that the programs they're writing are for users, and that there are certain things you can do to really frustrate users and other things you can do to delight them. We've got New Zealand work with app design. Yes, so the way the standards work is that they mix and match. So you can take a programming standard and a design standard and make a course out of that. And so it will depend a lot on the teacher and the school and local capabilities. But just bear in mind that the goal is not to have students trained up to be app designers. The goal is to train them to know what app design is and what the issues are that you need to know about design, you need to know about interfaces, you need to know about programming, and you need to know how to make them run really fast. Just to give you an insight into what these things look like, this is the level 1 standard for computer science. It's 3 pages long, and roughly half of it is just bureaucratic bump. And the actual key parts of it is just the bullet points that start here at number 2 and finish there. And you can see it's very underspecified, which gives teachers and students a lot of variation on how they do things. So basically, that excellence grade, the top grade, equivalent of an A grade that I was talking about, to achieve an A grade, they need to somehow compare and contrast the difference between algorithms and programs and so on. And they need to compare the costs of 2 different algorithms for problems of size n. And I'll show you an example of that in a minute. For the language thing, they somehow need to talk about how programming languages relate to machine language. And for interface, they need to compare and contrast related interfaces in terms of its usability. So just looking at the algorithms thing, for example, they don't need to be able to program an algorithm. It does help if they understand how an algorithm works, but there are programs that we've made available where they can download. So here is a sorting algorithm in Scratch that happens to be selection sort, and the cat tells you how long it took to do the sorting. So they basically run experiments with different amounts of input and just see how long it takes. And this is the whole scalability thing. So here's exactly the same exercise done using a Python program that they can download if they want. And it's got the selection sort algorithm there and the quick sort algorithm. Now, many of the students, and there's unplugged activities that explain how these work, but the real issue here is that, you know, for sorting 100 values, the selection sort takes 0.001 of a second, and quick sort takes 0.0003 of a second. Okay? Big deal. They both happen in the blink of an eyelid. But when we crank it up to, say, sorting 10,000 values, and this is the scalability thing, what if you suddenly had 10,000 customers or 10,000 things to deal with? Notice that selection sort takes 11 seconds, but quick sort takes 0.06 of a second. Somehow it's more scalable. And then if we take that 10,000 and double it to 20,000, our 11 seconds, like before, you might have thought, well, we'll double that. It should take 22 seconds. But no, it takes 46 seconds. In fact, selection sort is proportional to the square of the number of things that you're sorting. So if we double the number of things, it's going to take 4 times as long. If we have 10 times the number of things to sort, it's going to take 100 times as long to run. And they can run the program and actually wait for this thing to finish. I mean, 46 seconds is a long time to wait for something to finish. And when they're doing the HCI, they find out in actual fact that humans, around about 1 second is the limit. Because if someone's having a conversation and they stop for 1 second, like I just did then, people start to worry if something's gone wrong. And so a good interactive system will actually be working below the 1 second level. And so they'll know that 46 seconds is unacceptable. Whereas selection sort, here we go for twice as much data to sort, and it takes a little bit over twice as long. And so that's the key message there about algorithms, and there's lots of ways that they can explore those. At level 2 computer science, they start looking at how data is represented using bits, binary numbers. Of course, most teachers, if they're doing well, will introduce these things a lot earlier than just at level 2. And so that by the time the students get there, they actually are fairly familiar with these concepts. The problem is if you introduce it just when it's about to be assessed, then students very much end up saying, well, what do I need to do to pass the test? And just tell me enough to do that, rather than actually working and getting engaged with the concept. Another topic at level 2 is encoding, working out how things are compressed, the error correction that I was talking about, and encryption, and the fact that, what's enabled by encryption? What would our world be like if encryption wasn't possible on the internet, on disk storage, and so on? It's not at a really deep level, but it would be things like, with this barcode, that last digit there is a checksum, and that means that when you scan your can of baked beans in the supermarket, it's got a half a chance of working out if there's been an error in the scanning. Jim, so how much is HCI part of the curriculum? It's actually interesting that you notice that it appears once again at level 2, and so it is quite heavy in the curriculum. And yes, it does appeal to students who might be less interested in the techie side of things. And I think from an industry point of view, it's also the kind of person that they're really after, the people who can actually work with customers and design things that the customer really wants, but then also build those things as well. Yep, okay. There you go, I'm just pausing your question here. Many companies exploring algorithms for learning students. Okay. Yes, we do try and involve students in creating things, although what we find, of course, is that students generally don't know what they don't know. And one of the things that happened in some schools is that they just say, oh, our students know lots about Scratch and programming and so on, so I'll just give them the standards. And they can sort them out. And they just go off in completely the wrong direction. So you have a really bright student who is probably should get excellence, but they just didn't know that even that 2 algorithms could take different amounts of time, or in particular, they might assume that thing that twice the input will take twice as long and things like that. So there has to be a balance between sort of projects and getting students to explore things and so on, which is really important, but also just giving them useful information, like here is a way to do this, and these things exist. You might not have thought of this. And if anything, at the end, I think we leave them probably thinking, well, gosh, don't take anything for granted. We keep moving. So level 3, these topics are actually taken from the ACM curriculum. ACM is the big international organization for computer science. And they look really scary and freak out teachers no end. But most of them, in fact, all of them, we've figured out how to deliver in a way that is kind of fun for students and kind of engaging. And in fact, one of the things we've developed is this book called the Computer Science Field Guide, which in fact I gave a link to just before. And I'll just put it up again. So the thing with the field guide is it's free, it's open source. Google's paid us to write it. It's about a third written, but a lot of these topics are in there. And it enables students to explore these topics in a way that they don't have to be good at programming, but they do have to be good at thinking, and they do have to have a healthy curiosity and so on. It also comes with quite a few videos, and at the moment we've only got half a dozen videos there, and they're built into the field guide, but if you just want to see the videos, there's a link to them. And again, slightly humorous, and they're done by my own students who are just a few years out of university. And so the idea with that is that it communicates fairly clearly to the students what the topics are. Just getting back to the teachers briefly, we've surveyed the teachers quite a bit to figure out where they're at. And one of the really interesting things is that it's almost 50-50 male-female. This is a survey of about 100 teachers. There's probably about 400 people teaching computing in New Zealand. So this actually represents a big chunk of the people who will be teaching computer science. But look at the age range. It's probably not surprising, but most teachers are over 50 who are teaching computing. what is surprising, and a very pleasant surprise, is most of them are saying, this is really interesting, I want to get into this, give me the training and I'll do it. Because when you're over 50, it's time to learn something new and keep your brain active and so on. And also, they're used to computing being kind of a dumping ground for the weaker students. It's sort of like, we'll just go and learn how to do PowerPoint and, you know, stay out of the physics class sort of thing. Whereas now, computer science has become something that the top students should be aspiring to. And so, like, we asked the teachers, what's your programming ability like? And you'll notice, for example, you know, 12% of the teachers back in 2012, when things were just starting off, couldn't even program. And most of them said they had rudimentary skills. But notice just 1 year later that their confidence has improved. And that also applies to their confidence about assessing and teaching. So again, just the year after these were introduced, most of the teachers were saying they were unconfident in this orange area here, but just a year later they built up a lot of confidence from training, and that makes a big difference. Now, it all depends on teachers making the change, because if they don't want to do it, it's not going to happen. And we asked them, why did you do it? And nearly all of them were motivated because of the students, or because they were interested, or it's just the right thing to do. It's good for the country to have more computer scientists and so on. Almost none of them were motivated because the management said, this is a good idea, we should get into this. In fact, most of them have been fighting management, because management say, well, we've got iPads throughout the school, or we've got computers in every classroom, or everyone, you know, even my 8-year-old knows how to use PowerPoint, so why do we need to teach computer science? And that's been a lot of work. Okay, so teacher training, in fact, we'll jump straight to that. So the way that it's happened, this is from the survey, the number one source of help has been online discussions amongst teachers. So, because there's half a dozen of them who are well qualified in computer science, just half a dozen in the entire country, but they have obviously been trailblazers at the cutting edge, and they've shared what's worked for them. We've also been really fortunate with CS4HS, which actually started in the US. It's Google sponsored, and they have run 2 or 3 day workshops, or at least they've paid us to run these 2 to 3 day workshops once a year. Not very long, but it's enough to get people quite a leg up, and that's been really important. And we've noticed that the difference, we'll get teachers coming in saying, well, it was 3 days of free food, so I might as well come along. And at the end they go, I can't wait to do this stuff with my students, because they've been empowered with the tools to do it. Sadly, you know, the government contribution is not so great, again, because the bureaucrats don't really fully understand it, and of course people don't spend money on things that if they don't have to if they're in government. But you know, so here is just a few sample teacher comments from the survey. So, you know, for the first time in many years, this final year programming class has able students in it, which is, you know, quite an indictment on how things used to be. And teachers are regaining passion and enthusiasm, but it's not all fun. You know, top academic students have fun, but low ability really struggle now, because what used to be a good, easy course to do is now something that's academically challenging. And if you don't have entry requirements, then you get a mixed bag of results. And so we asked them, did you attract a significant number of highly capable students? Yes, that happened for many of the teachers, but also many of them attracted students that weren't able to perform well because of those misunderstandings. And in fact, 12% of them said they ended up with both groups of students, which is really hard work. It'll take a while for the culture to develop where people realize that this computer science thing is a great challenge, good for the top students, but not so good for the weaker students. But one of my favorite comments ever is, this is the teacher workshop that I was talking about, CS4HS. Best 2 days I've spent on PD, learned heaps, haven't laughed so hard, drank as much wine in a long time, gave me a new passion for the subject I teach. And so if we can, you know, give teachers that new passion, that's fantastic. The training the teachers in these new topics is really important. Oh yeah, we include wine in the PD, yeah. Pizza and wine, whatever it takes to get the teachers across the threshold, we'll do it. It's not true. If there's time, I'll tell you a funny story about the wine, but we'll get back to that another time. So in this field guide, I've given you the link. We've got these videos which introduce the topic. So computer graphics, which is, you know, there's a bit of maths in there, moving the objects around in 3D space and so on. software engineering. Oh, by the way, and also the people doing these videos, this is Rem. He actually wrote a lot of the activities that are in the computer graphics chapter. This is Yanina, who was that PhD student who's now doing a PhD at Cambridge, and she's studying software engineering, so she did the video about software engineering. This is David, who did one about computer vision. And actually, within the web browser, you can actually do some computer vision and get students to do experiments and so on. We've also set up this club for younger students, because not all schools offer this sort of thing, and not everyone can access it. Not all teachers want to offer it, and so on. And so for younger students, we've ended up with, it's just bursting. We sort of had more and more groups, but we've developed a badge system. It's in cooperation with Peter Denning in the US, who actually came up with the idea. So effectively, it's a pilot for it. But it's one way to circumvent the school system. You just start up a club, and it's actually very similar to what I was talking about before with what's in NCA's in our standards for the high school students. But they can do it as part of a club and earn badges. But you know, the teachers are absolutely crucial, and getting them on board. And we start with so many teachers who are very, very nervous. But, you know, their job is under threat. Their credibility is under threat. You imagine you don't quite know how to program, you don't really know what this computer science thing is, and suddenly you have to teach it, and the management don't even want you to teach it, and the students don't have respect anyway, and so on. And where do you get? And so the very big part of our job has been to take teachers from being kind of very nervous, wondering whether it's time to retire or, you know, move to a different area or something like that, and get them really enthusiastic about it. And I've been really pleased that most teachers make the transition, and as long as you give them the resources and the training and so on, they'll do it. And they've done it on the smell of an oily rag. They're really, you know, put a lot of their own time and resources into it. Coder Dojo, yes, the clubs, they're a little bit more structured than Coder Dojo, but the key thing is there's Coder Dojo and Code Club and Code Academy and things like that, very focused on programming. The Computer Science Club has the programming still as a core kind of thing, but it has these, and you can get a badge in programming, but you can also get a badge in algorithms, in artificial intelligence, in formal languages, in interface evaluation, in all these other subjects in computer science. So what we've found is, you know, 3/4 of the students we get love programming. They love playing with computers. That's fine. They're the ones that would do fine in Coder Dojo anyway, and it just keeps them enthusiastic and helps them to meet like-minded children. Really, really good. But there's a quarter of them who go, well, I don't really see the point in programming, and more often girls than the boys as well. And, you know, it's not for an end in itself, but you expose them to the other ideas, like let's evaluate interfaces, or let's work out cool algorithms for things. And by the way, you'll need to write a program to make that happen. And suddenly they can see the point in programming, and they're really interested in computer science. So it's not programming for programming's sake. And I think that's really important to give them that broad view, which actually brings us back to where I started. Helping young children to really discover what they want to do is the goal, and just, you know, give them lots of opportunities to explore this. And by the way, with the club, and obviously with these courses, a percentage of them, you know, 5, 10, 20% don't make it. It's not their thing. One of my favorite emails, not favorite really, but a really telling email from the parent was, thank you for offering the club. It's a really good idea, but our son Jack, we discovered that he really likes computers, but he doesn't like computer science. And to me, that's just as valuable as saying we found out that our daughter actually really loves computer science and she didn't think she did. And in both cases, we're helping students to explore and figure out what these careers are. And it may be even that young Jack, when he matures a bit more, will realize actually maybe he does like the computer science stuff and he needs it. But there are so many kids focused on using the computer and the computer as an end in itself that they don't get to think outside that box. So there's a whole bunch of URLs. Some of them I've already provided you with. And the first one is the field guide that is still under development. We'll be writing a lot more over the summer, which is, of course, December and January for us. The club, a little bit of information about the club. It's going to be reinvented next year. We're gradually working out what works and what doesn't, and so we're going to try and turn it into something that actually can be used internationally and could be used in conjunction with Coder Dojo or Code Club or something like that too. So it'll be badges that people can use, but we're going to work on how to make that a bit more scalable. CSANZ is the Computer Science Association of New Zealand, where we provide information for schools and kids about what's actually happening. In particular, there's a brochure there because for parents, aimed at parents and guidance counselors and kids, that basically says, hey, this new stuff exists. And then it's the Teachers Association. Without being a member, you can still see a lot of their material, but paid membership sort of gets access to a lot more resources. And then the Unplugged project, which was aimed more at junior students, and the elements of that are coming into the high school stuff, but that's something that we're going to start looking at using now that these ideas are flowing down into the junior schools. So I will stop talking at that point, and do we have a moderator or questions or discussion? Yeah.
Hi, Tim. It's Lucy Gray. Thank you so much for presenting today. We really appreciate it, and you're very engaging and inspiring to us all. I'm actually going to ask somebody in the audience who's very good with questions to see if he has any for you. Jim, who's our co-chair from HP, has been very interested in your presentation. And I'm wondering, Jim, do you want to take over and ask some questions? Because you've been very thoughtful throughout all of this.
Happy to, and of course I'm not the only one with questions, so I want to make sure that anyone else in the room that has questions that haven't gotten answered, make sure you either raise your hand or type them in the chat. But Tim, I am curious if you are connected at all with Iris Lipinski and Apps for Good. You know, Apps for Good is a UK organization that grew out of CDI International. Their focus is computers. Well, so they're coming at it from a whole other angle, which is it's not really about the app programming. It's about the app design and thinking about doing good things in your community by developing an app. And they actually introduce this concept to students, and they go through the whole design process without the coding. And then later on, the older kids actually learn how to do the coding. And it seems like that your world and their world would be a really interesting meld. Have you worked with them at all?
No, I haven't worked with them, and we are aware of what they're doing, and there's a couple of other related organizations as well. And I mean, at the moment, it's been just all hands to the pump to just help the teachers and get things up to speed and so on. But long term, I think things like that are fantastic as motivators. And particularly one of the things we're doing with the Computer Science Club, again, it's only been going for 2 years, but as students get older and more experienced, one of the criteria in the badges is that they must help younger students in order to get senior badges. And I think something like Apps for Good would be a brilliant example of how to put wheels on that in a motivating way, you know, rather than just teaching a concept for the sake of it. You're actually got a project that everyone's working on, and the younger students need help from the older ones with implementing it and things like that, and that would fit in really well with that sort of thing.
Yeah, yeah. Oh, Iris did present a keynote that was recorded 4 a.m. my time this morning, so I didn't make it. But,
right.
If you are interested in hearing her talk about what they're up to, you can find that one.
Yeah, thanks. Actually, that is really good. The thing I love about this conference actually is it's going to be a very rich selection of material available at the end.
Yeah, I'm dying to see all these other things I've missed. So it's fantastic. Let's see, what other questions do we have from the audience? Let me scroll back here and see if there's some things that we missed. If we missed something, retype it in the chat if you would. Tim, while people are thinking, another thing I've run across is that there are some folks that are crying out to make programming a required element of graduating from high school. What's your thought on that?
My thought is that I don't know if we know yet whether that's a good idea or not. And even the whole computational thinking thing, I think it's really good for people to know about it. But one of the analogies I sometimes use is with empathetic thinking. So I would love it if every graduate had empathetic thinking as a requirement, because they would be such better citizens. But to some extent, some of that's pre-wired into people. Some people are naturally empathetic, and some people, I think, are more naturally computational, and other people see things quite differently and bring completely different skills to the table. And so there's that issue, and then the other issue is that as soon as something becomes required, then and the teacher has to teach something and they're not passionate about it, then you end up communicating that it's an uninteresting subject that just has to be done. So there's actually a risk that it could actually do more harm than good. Now, that's the reasons why maybe not. I mean, obviously, the argument the other way is that it's a fundamental skill these days, and there's David Rushkoff's whole program will be programmed thing, that it's so empowering to be able to program and change things and so on. But I don't think we know yet whether that's a good idea or not.
That may, in fact, be an argument for not having any curriculum. But anyway,
well, sure.
yeah, we'll leave that one aside for a moment. Yeah.
Well, actually, no, that is an interesting one because in New Zealand, the only things that are required are maths and English, and so you could choose whether you're going to go into science or art or languages or whatever, and so students gradually find their strengths. Whereas I think I get the impression in some countries it's a lot more prescriptive, and you must do more than just a few basic subjects, which is good from a liberal arts point of view and broadening the mind and so on. It can become too narrow if students have too much choice, and that's just a real challenge of working with teenagers, I think.
Right. What other questions do we have from the audience? Anybody else? This is a rich topic here. Tim, do you have any thoughts to, I mean, there's so many different, the actual technologies of programming and computer science keep changing. How do you keep up with it? Or does it really not matter? It has more to do with thinking about the logic and algorithms and the actual programming languages. Let them change, it doesn't really matter.
Yeah, well, that's something we've had to tackle here, of course, because teachers keep saying, what language should I teach? And I've actually come to the point of saying, well, first of all, a language that you're really confident with, because, again, the teacher's confidence will have a huge influence on how well students learn. And one of the biggies here is that 30 years ago, teachers were teaching Visual Basic, or Basic. And these are the same teachers who are now 55 years old, and they feel really comfortable with Basic. And it's fine, you can teach all the main concepts in programming using Basic. Now, a lot of people go, oh, that's so old and it's, or inappropriate and it's not used in industry and so on. But what we're trying to do is enthuse students and just get them to learn the ideas that you've got, branching structures and looping structures and variables and so on. I mean, there's plenty of time to learn about the real details of object-oriented programming and serious languages, that industry use and so on. So that's the first thing I would say is stick with something that works well. But the other thing is it's really important that there are good educational resources for the language. So that's why Scratch is so popular, and even Java has done quite well because there are so many books about Java. But Java is a really tough language for a beginner, and Python is taking over in New Zealand, for example, and as a beginner's language, and it's got a lot of advantages. It's also got some disadvantages.
Yeah, I guess this is good to the point here that folks are asking in the chat what can be done with younger students or adult community centers in places like Africa. What would you recommend? Scratch as a starting point? Or?
Well, for programming, I think the jury's still out on Scratch as well. I mean, it's fantastic. I love it, and we use it a lot, and it's a great way to get students engaged. But there's a real risk with Scratch and also Alice, sort of its cousin, that students see it as just an animation system. And so and as a sort of a smorgasbord system, you say, oh gosh, I can make sounds, so I'll do that. And what they're missing out on is learning how to plan a program. So I think that it's great for introducing what programming is, but it may not be so good for teaching how to do programming.
Interesting. Because I've seen people using Scratch to program Arduino boards to make, e-textiles and things.
Yeah, and that's fantastic because that becomes purposeful then. They've got a goal in mind rather than saying, oh, yes, I could put this together and come up with something. And Sue mentions, teaching Scratch to 5 or 6 year olds. I mean, that's great if it's being taught by an enthusiast and so on. But there's this really interesting question: is it's possible to do it, but does it make any difference? And it may well make a difference if kids grow up being aware that they've got that control over the computer. That's something that I think we're still figuring out.
Well, it's just before the hour here, and I've got 3,000 other questions I could ask you, but I think in all fairness, I think it's a good time to simply say thank you. And I wish you a wonderful day there in New Zealand as we sign off. it's terrific that you could join our STEMXCon, and hopefully our paths will cross and we can do this again. It's really great to have the cross-fertilization from across the thousands of miles. So thanks for joining us, Tim.
That's a real pleasure. Thanks for the chance to share all that.
Great, and thanks all you for being in the room here. I'm going to turn off the recording and then have to boot you out of the room in order to make the recording actually get uploaded or whatever. So thank you, everybody. Really appreciate it.
Thank you.